In week 3, I want to kick this off by talking about geological structures. The rocks around Kingston include the limestones we've been talking so much about from about 460 million years ago, but beneath that, the colorful rocks in this map are older than 1.3 billion years. After 1.3 billion years, there was a major supercontinent collision, and the Grenville orogeny was born. This was an enormous mountain range that spanned pretty much all land masses on Earth, and Kingston was right in the middle of it. This was the largest mountain range the world has ever seen, and it was central to the formation of the supercontinent Rodinia. This mountain range stood 15 to 20 kilometers above the rocks that are now exposed around Kingston. So behind me are some gneisses. These are metamorphic rocks. And about 1.1 billion years or so, there was a major mountain building event. Above my head would have been many kilometers of mountains similar to the Himalayas. And these rocks would have been compressed, and you can see the vertical fabric, which is a fabric formed from compressing these layers. And you can see this fabric running up and down the rock. This is a rock compressed this way, forming these plains, this foliation plains. Here's a great example of a metamorphic gneiss. This used to be sedimentary rock. What you're seeing there, though, these lines here are not the bedding, but they're joints that follow the plane of the foliation. This rock was compressed in this direction, and that fabric from the gneiss now causes planes of weakness. Here you can see the foliation plane on the left, and a joint on the right has created a wedge that has failed and fallen onto the roadway. Here's another example of that gneiss that would have formed during what we call the Grenville orogeny, the Grenville mountain building event, about 1.1 billion years ago. Here's an example of a small fault running through this Precambrian gneiss. This plane of broken rock indicates a plane of slippage, of shear, at some point in the history of this outcrop. Here's some beautiful folds within a gneiss. This fabric would have been compressed in parallel foliation planes and then remolded and refolded by geological pressures. Here's another example. You can trace this one straight layer. This is folding. Here's another one. You can follow it down, and here, there's a little quartz layer. Again, beautiful folding. These structures I've been talking about have to do with this mountain range, the Grenville Mountains above Kingston. 750 million years ago, this is what that might have looked like. The Grenville orogeny was still very much in play. You can see that dark stripe running across through the star, which represents the city of Kingston. Around 600 million years ago, all of Kingston was under ice, and large multicellular life evolves in the ocean for the first time. Supercontinent Rodinia begins to break up. About 540 million years ago in the Cambrian, Kingston was sitting just on shore. Meanwhile, complex animal life with eyes, teeth, and legs evolves in the oceans. This is the Cambrian explosion. And this is the formation of those sandstones that we looked at in earlier videos. Those Cambrian sandstones, just as Kingston moves offshore as the continent begins to sink. About 470 million years ago, Kingston has moved farther offshore. We start to see shales and limestones being deposited. We've looked at those last week. We also see the first vertebrates in the ocean. Keep following the star, that's the city of Kingston. 450 million years ago, we see an island arc of volcanoes starting to approach Kingston due to the subduction as this proto-Atlantic begins to close again. Kingston is a calm sea. We see limestones and dolostones deposited there. The shales that are underneath Toronto were formed at this time. This island arc is the Taconic orogeny. It's the first part of the modern Appalachian Mountains developing on the east coast. But 430 million years ago, we see another island arc, another subduction ridge approaching the continent. This is the Acadian orogeny, which is the middle of the Appalachian Mountains. First land plants are seen at this time, and the rocks that are on top of Niagara Falls are deposited 400 million years ago. Rocks at the surface in Western Ontario being deposited. The African continent, which is part of Gondwana, is approaching from the east. Sharks have evolved. Animals are now happily on land. Late Devonian, 370 million years ago, Africa begins to collide with North America. Folding, jointing, faulting that we see in the limestones and gneisses around Kingston begins at this time. So the rocks that were deposited around 460 million years ago are now starting to deform. Hi there, I'm up here at one of my favorite places. This is my cottage up just north of Kingston here. And it's founded on, you guessed it, Precambrian gneiss. Now if we want to look a little closer here, you can see some very interesting structures. You can see joints cutting this way and this way, and they don't make 90-degree angles to each other. This is the effects of shear during the tectonics, maybe some 400 million years ago, creating these systematic fractures called joints. These are shear joints. They're formed in compression this way, and you get these two planes forming shear joints. There's actually a fault running through this little bit of shrubbery here, separating what is more of a granitic gneiss on this side from a metasedimentary gneiss on this side. There you can just see the trace of the fault running into the water just here. So these two pieces of rock have moved with respect to each other along this surface, and that fault goes out into the lake. So now we're going to look at some joints. We're back at this cyanide outcrop at Joyceville Road. Behind me you can see this flat surface. This is a natural fracture that was caused by tectonic forces over a long period of time. This is not a random fracture caused by the road construction. And if we wander down this road cut, you can see a number of natural fractures throughout the rock. There's another one. Let's get up a little closer here. You can see this flat surface above me. These are joints, and they occur in sets. Here you can see joint sets dipping this way and this way. And there's also a horizontal set that runs across the outcrop. If we want to measure this joint as an engineer, because we want to be able to put these orientations into our models to look at things like slope stability, groundwater flow, foundation stability, etc., the first thing we would measure would be strike. And we use a compass. We level it so that it's running along the direction of strike. That is the horizontal intersection of this surface. And so now the compass is pointing down strike. And then the next thing we do is we measure the dip. So we put the compass vertically, and there's a small little adjustment that can be made on the back, which measures the inclination of that surface. And together, we have strike and dip, which defines the orientation of this plane. And we would repeat that for all the different joints in the outcrop, and that would feed into our computer models for stability and other applications. And here we are at the Berryfield outcrop on Highway 2. Here you can see that the bedding, it's inclined, and then as we get down, you can see that it bends over and folds. There's the fold there, and there's the hinge. So this limestone was deposited in the Ordovician, but then folded and jointed during the building of the Appalachian Mountains on the East Coast. Both the fold and the joints that you see were formed about 370 million years ago. Here you can very clearly see the vertical joints in between the bedding planes of the limestone. These were caused by tension as this fold was forming during the Appalachian orogeny. This surface behind me is actually a small fault that's cut through some of the bedding in this limestone. At the same time as the joints were forming, at the same time as the limestone was folding, something had to give. And so this surface here is a very small fault that's formed between maybe about 10 meters worth of bedding. There you get a great view of that fold. Bed's curving up over the hinge and then down the other side. These beds were formed perfectly horizontally and then folded during compression as a result of the Appalachian Mountains being constructed. So let's look at the rest of the tectonic history of Kingston after this structure was formed. 340 million years ago, Pangaea supercontinent is forming in earnest. Kingston moves back up onto land and erosion begins and continues till this day. So 300 million years ago, these mountains are at their peak. Kingston is just on shore again and at the equator. More erosion happening. North American coal fields are developing in these shallow seas and swamps. Early reptiles and giant insects. 280 million years ago, the Appalachian Mountains have reached their peak altitude. Pangaea is fully formed by now. 260 million years in the late Permian, Kingston moves north. We start to see the Appalachians eroding back down. And at the end of the Permian, we have a mass extinction of 90% of life on Earth. 240 million years, most of Canada is on land at this point, and this is the rise of the early reptiles. Into the Middle Triassic, 220 million years ago, we see the first pre-dinosaurs and the first beginnings of fractures in the supercontinent of Pangaea. Those fractures grow into what eventually will become the Atlantic Ocean as Pangaea begins to break up in the late Triassic, and we see the first true dinosaurs 200 million years ago. In the Jurassic, 170 million years ago, dinosaurs are thriving, mammals and birds have evolved, and you can see just south of Kingston the Atlantic Ocean beginning to open. 120 million years ago, there was no ice on Earth. The maximum sea levels reached at this point, and if you look to the left of Kingston off the continent, you can see the Rocky Mountains beginning to form. 105 million years ago, Tyrannosaurus rex lives. All topography around Kingston is pretty much fully eroded at this point. 90 million years ago in the Cretaceous, a shallow sea opens up in the Canadian prairies and Midwest. This allows dinosaurs to wade out into the mud, die, and get preserved by sediments. This is why Drumheller in Alberta, for example, is so famous for dinosaur fossils. Offshore of the Rocky Mountains to the west, the BC coastal mountain ranges form. 66 million years ago, late Cretaceous, this is a mass extinction of all the dinosaurs caused by an asteroid impact. You can see the black dot where the arrow is pointing. That's the crater of the impact just off of Mexico. 50 million years ago, the age of the mammals. 33 million years ago, primates evolve. The Antarctic ice cap reforms in the mid-tertiary. 15 million years ago, hominids first appear in Africa. The Greenland ice cap forms again. And here we are nearing the present. The Pleistocene, which is the early Quaternary, and the Holocene, which is since the last glaciation. The last glaciation finished about 11,700 years ago, but dozens of glaciations over the past 2 million years have eroded the Canadian landmass, especially in the Canadian Shield and in the Kingston area, down to what we see today. All going to produce this fabulous map that we've been seeing throughout the course.